I've known Bill longer than most people in this room. Maybe Steve has known him longer. But I met Bill at a conference in Germany in the 80s when he came to talk about aspects of gravity and gravitational radiation. Other people in attendance were Weir, Glauber,
Wigner,
and so forth. So I got to hear this young man's lectures and was very, very impressed by him, and got to know him better over the years. The more I know him, the better I like him. For example, he comes from the University of Winnipeg, and that's great, especially since I come from the University of Wyoming, about the same. His interesting undergraduate trajectory is characterized by the fact that he wanted to take a graduate course. So he went to the chairman of the department and said, "Oh, you can't take that course. I wouldn't let anybody into that course who didn't have at least a 95 overall average." And Bill said, "Oh, that's good luck for me. I had a 96 overall average." So he got into a focus of course.
this was just a math, even an undergraduate math course he didn't want me to take
That's good.
because it was useless taking mathematics courses.
Well, he has gone on to have interesting discussions and arguments with lots of people. He is a person who can make contributions to, say, quantum computing back in the 90s when the influence of coherence was not well known. So an interesting article in his rev that I didn't know about. Has had public confrontations with lots of people, including Eugene Wigner. Now, we've always said that if you get into an argument with Eugene Wigner, you've lost before you ever started. But Bill actually won this argument because he had the sympathy of all of us in the audience. Eugene Wigner, you know, is the guy who, when Oppenheimer, who destroyed, was trying to lecture at the Princeton Institute of Advanced Study. Wigner got up, took the chalk, and gave the whole lecture. This is the way Eugene was, and many years it was. In any case, I've learned a lot of physics from Bill, and I imposed on him to give this lecture today. So join me in thanking Bill for doing that.
This lecture is about ancient material. This is not new material. I got a little bit interested in the history of general relativity, etc. Also wrote a paper on Kepler, Newton deriving a discrete version of Kepler's laws and exactly how those arguments went through. But I was trying to understand why in the world it took so long for people to really understand the Schwarzschild metric. So the history, okay, I'm going to have to do it that way. The history was that Einstein published his paper on general relativity in November of 1915. He had finally gotten the final ideas after having wandered around in the wilderness for about 5 years, trying to figure out how to develop a theory of general relativity. He very early on felt that the metric was the way to go, but he kept making mistakes and getting lost in those mistakes for a year at a time or so, and then coming back. He first had the idea of producing a theory that was coordinate invariant, and then decided that that didn't work because he calculated the rotating coordinate system, the rotating disk, if you will, in that coordinate system, in the rotating coordinate system, and discovered that it didn't satisfy the equations. He had simply stuck in an extra factor of 2 into one of the terms, and as a result got the wrong answer, and stubbornly refused to listen to Bessel, his good friend, who pointed out that maybe there was a problem with this, and finally, about a year later, discovered his problem. Anyway, so about a few weeks before he finally published his paper, publications were very, very rapid in those days, he finally got the right theory. There was this guy, this physicist, who had volunteered to fight in the German army. This was, middle of the First World War. He was made an artillery officer and sent out to the Eastern Front, i.e. fighting against the Russians. He promptly got sick, an autoimmune disease, in the trenches, and so was spending his time in the field hospitals. He had Einstein's paper sent to him on the front, and in late 1915, he started thinking about it and started calculating. And by March, he had published a paper in which he found the first exact solution of Einstein's equations. The best that Einstein had been able to do was to calculate the linearized equations. As I'll mention later, he sort of messed up because he had strong prejudices as to what the answer should look like, and they turned out to be not the best prejudices to have. Anyway, Schwarzschild derived this metric that I've got written down there. And that metric had some weird features. The first thing is that R in that metric here, the omega squared is d theta squared plus sine squared theta d phi squared. So that's just the metric on the surface of a sphere in the usual polar coordinates. And R squared basically measures the circumference of that sphere. And so that gives you one of the coordinates. But when Schwarzschild derived the answer, he got these funny terms in there. One of them was 1 minus 2m over r. M was just a constant. If one goes very far into the linearized regime where 2m over r is very small, linearizes this metric and looks at the orbits of planets around this, then m turns out to be the mass of that, of this solution. It acts just as though it's actually gm over c squared, but I will of course be using units in which g equals c squared equals 1, sometimes also equals 2 pi. And later on, I'll also be choosing units such that 2m is equal to 1. So those are the sort of, g equals c squared gives you 2 of the relationships, and m equals 1 then determines all of the sort of dimensional quantities within the theory. And you had this weird behavior that this coefficient multiplying the time went to 0 at r equals 2m. Furthermore, this second term here goes to infinity at r equals 2m. And this bothered them. Nobody understood it. Nobody understood what this was all about. Einstein, as years went by, thought maybe this represented sources of matter. that at r equals 2m, there was some sort of sphere or sheet of matter that was creating this gravitational field outside the matter. This one, R, the term dr also looked really weird. And there were many, many confusions that ran around. Now, Lanczos already had recognized that singularities like this could come from just bad choices of coordinates. Lanczos, he's a mathematical physicist.
Where was he?
Pardon?
What university? Or what was his other contribution?
I'm not sure. I mean, he was one of the top mathematical physicists of the very early part of the 20th century. But, you know, this lesson, in a sense, didn't sink in. In 1921, oops, I got to do it this way. So yeah, in 1916 already, it was realized by Ludwig Flamm that the problem was not the dr over 1 minus 2m over r. One could do a change of coordinates, just a radial change of coordinates, which showed, in fact, that you could embed this into a three-dimensional flat space-time. And what you got out of that was a paraboloid. So here's a picture of that. And here's the paraboloid. It's a paraboloid of revolution. And you could also extend this paraboloid off in this other direction. For example, if this is axis, you call this axis W, then you got the equation of motion for the spatial part of this whole spatial part of the metric is simply, you can write it in this form where W is another coordinate, and the relationship between W and R is that R is equal to W squared. That's just a paraboloid. And then you had the theta and phi, so you get basically a paraboloid of revolution. Notice that this can trivially be extended to negative W, and you get another paraboloid heading off to infinity there. This is just a wormhole. And Flamm, in fact, recognized this in his paper. Some people has found his paper difficult to read. I'm not sure why. But this was already in 1916. So the metric, the spatial part of the metric was completely regular. It was just that you were using this rather unfortunate choice of coordinate, namely R, instead of something else. R is, of course, got this physical meaning of being the radius of these spheres of symmetry. So it sort of had a physical meaning, but for this particular problem, or for looking at this particular problem, it wasn't the most convenient choice to choose. And this sort of disappeared. I never even heard about Flamm until Kip Thorne brought it forth in his movie, and he had discovered it. And in fact, if you read his book, the metric for the little black hole or little thing, wormhole basically, orbiting out near Saturn is exactly the Flamm metric. With instead of 1 minus 2m over r dt squared, you just stick a 1 dt squared. It's a perfectly good solution. Well, perfectly good is maybe arguable because it has negative energy densities in order to create that solution. But never mind that. And it's really just the Einstein-Rosen bridge. Now, I've got real trouble because this was something published on his favorite theory just after he had proposed the theory. I'm positive he would have seen it. It wasn't in some weird journal somewhere. I'm positive that he saw it. When he and Rosen wrote their paper on wormholes, 20, little under 20 years later, they never referenced Flom. And there's still a lot of nonsense talked about even today as far as this is concerned. Now, let me spend a little bit of time on what has been called the Rindler metric. As I'll mention later, its origin is not due to Rindler, but he was the one that basically popularized it and made everybody know about this metric. It was given the name Rindler metric and Rindler coordinates by that gentleman that sits right there in the middle of the.
How do you plead?
Guilty. The evidence in the papers is clear. Now, so let's have a look at this metric. This is like the radial and the temporal part of the Schwarzschild metric in some coordinates in which the radial part of the metric, like W or something, is not singular. This metric, however, can be transformed by a simple coordinate transformation. What?
Units, because I mean.
Units?
Yeah,
Units
like
are units I will take such that 2m equals 1. So everything is dimensionless. Notice that this looks like something that you're all totally familiar with, namely angular coordinates. If you ask what is the metric on a two-dimensional surface where you use the angle phi as one of your coordinates and the radius from the center as the other coordinate, the metric just looks like dr squared plus r squared times d phi squared. Well, this looks just like that, d rho squared. Well, there's a minus sign in there. That minus sign changes then to transform the r squared, dr squared plus r squared d phi squared into ordinary Euclidean coordinates. Of course, you take r times cos phi and r times sine phi as being x and y coordinates, and then you get the usual Cartesian coordinates with the usual Cartesian metric. Similarly here, instead of using sines and cosines, you use coshes and sinh, because you're going to have something minus something equals 1, and something minus something, something squared minus something squared equals 1 is hyperbolic sines and cosines. So this is just flat space-time. So treating it this way, we get a flat space-time metric here. One can always also do it in another way. For example, let us define null coordinates. What do I mean by a null coordinate? A null coordinate is the path that a light ray would follow. In special relativity, we know that the length of a light ray is 0, no matter how long it is. And here, if we solve the equations for how light rays would travel in this metric, we get that we can define null coordinates, little u and little v, which correspond to light rays traveling in opposite directions. And then if one does that, one gets a logarithm of rho coming in. We've got a rho squared. Well, rho squared is just e to the twice logarithm of rho. So if we add u plus v, you get twice rho, twice log rho, exponentiate that, and one gets a metric These are the capital U's, which are the exponentials of these little u's, and capital V is the exponential of the little v. And one gets a metric which just looks like du dv, which is flat space-time in these null coordinates. Or if one takes v plus u over 2 and v minus u over 2, that should have been over 4, v minus u over 2, this is going to look exactly like dt squared minus dr squared. So these are tricks that one can play with the Rindler metric. And those are the tricks that people finally started using. However, there's an interesting aside. In 1921, both Gullstrand in Sweden and Panleve in Paris found new solutions. These were solutions for a spherically symmetric system and a time-independent system. Notice one thing, this metric has these an off-diagonal term in the metric. Einstein didn't like off-diagonal terms. He didn't know what to make of them. Anyway, they had these off-diagonal terms in the metric.
Why do you say that? By going to a rotating frame, flat space-time has off.
He didn't like them. I mean, what can you say? It's too bad because he could have been the first to solve the exact equations trivially if only he had done off-diagonal terms in the metric, but I'll come to that later. Anyway, they got these and they said, wait, Einstein's theory is nonsense because I've given exactly the same conditions, namely time independent, spherical symmetry, and I get a completely different solution. Obviously, this theory is not a well-defined theory. It gives you lots of different solutions for exactly the same problem. This is not physics. Einstein was invited to Paris to discuss this with Panleve, and he emphasized, he says, look, my theory is coordinate invariant, and so I'm allowed to change coordinates. And what you found must be a coordinate transformation of Schwarzschild. As far as I know, neither he nor anyone else at that time actually showed that. And furthermore, because of this off-diagonal term that he didn't know what to do with, he forgot about this. Notice that the name Gullstrand comes in here. Gullstrand was an interesting character because he was part of the Nobel Prize Committee. And Einstein had been suggested for the Nobel Prize for about 10 years. He was put in charge of looking at the relativity part of Einstein's theory, both special and general. And he just said, this is all nonsense. Both special relativity and special general relativity was all nonsense. And so Einstein's Nobel Prize got delayed by basically 10 years until 1922 because of Gullstrand's opposition. One of the little stories is that he was in America at the time that they awarded the prizes, and he came back to Germany, and the Nobel Committee wrote to him and said, okay, the king has said that he would be interested in presenting the prize to you personally, and he'll come to your place and give you the prize. But we must emphasize you are not to talk to him at all about relativity, either special or general. The king arrived and said, what's this about relativity? Well, you can't argue with the king, can you? So Einstein argued it was just coordinate freedom, but as far as he knew, as far as I think anybody knows, he didn't actually demonstrate it. That took another 10 years to do. In 1922, Eddington also showed that there was another solution, which is different from the Goldstrand-Painlevé solution. And I believe that Eddington did recognize that, although that's not entirely clear, as simply a coordinate transformation of Schwarzschild. And he had a metric that looks like this. Has an off-diagonal term instead of the square root of r, it has a 2 over r. The radial part has 1 plus 1 over r in front of it instead of 1 over 1 minus 1 over r. The time one is the same as before. But if you look at this and you set r equals 1, i.e. r equals 2m, in this equation, this term, of course, goes to 0. But this term is 2. So if we write the metric as a matrix, and this term is also equal to 2. If you write it as a matrix, it's got a 0 in the top left-hand corner, a 1 in each of the diagonals, and 2 down on the bottom of this 2 by 2 matrix. Well, that's a perfectly regular matrix. Its eigenvalues are plus or minus the square root of 2. Its determinant is fine, etc. It's a perfectly regular matrix. So the metric is a perfectly regular metric. And so this shows that r equals 1, r equals 2m surface is in this coordinate completely regular. I don't think Eddington never made any comment about that, nor did anybody else. Eddington was interested in comparing Einstein's theory with Whitehead's theory, and that was the whole purpose of it. There was a very brief paper that he published about this. Now,
notation, d omega squared is the same as your.
That's d theta squared plus sine squared theta d phi squared. Yeah, just so I don't have to keep writing out that term. Now, there is a metric that we call the Eddington-Finkelstein metric, which if you go into textbooks nowadays, everybody talks about. Neither Eddington nor Finkelstein ever wrote it down. That was, as far as I've been able to tell, first done by Roger Penrose. He wrote down a coordinate transformation of the Schwarzschild metric. And this was, of course, back in the 1960s already, so this is long after these confusions. And basically wrote down this metric, which we now call the Eddington-Finkelstein metric, which should probably be called the at best the Eddington-Finkelstein-Penrose metric. It's a sort of almost trivial coordinate transformation from the the metric that they had, i.e. you replace dt by dt minus r, plug it in there, and you get this, or call u equals t minus r, and you get this metric here. Finkelstein, well, that was 1958, completely understood that his coordinates made r equals 2m regular in some sense. You could go across that. The coordinate system went through that surface. Actually, it turns out there to be two surfaces, and they're different from each other. One you can go across into the future. The other one you have to go into the past to go across. Finally, 1933. 18 years after Schwarzschild, or 17 years after Schwarzschild, Lemaitre came along. He was a very bright guy. He was a Jesuit priest, got extremely interested in cosmology and so forth. And he not only proved that the Painlevé-Goulstron metric was coordinate transformation from Schwarzschild and explicitly wrote down what the coordinate transformation, and also introduced a new set of coordinates, which I'll call tau plus or minus and sigma plus or minus. In other words, there's two sets of coordinates, these tau and sigma coordinates. And R is this rather uncomfortable form here. And T is given by sort of the tau plus or minus various terms which have logarithms in them and so forth.
Would you comment how did they discover these complicated coordinates?
One can make it reasonable to do so. The Painlevé-Goulstron, I don't know how Painlevé and Goulstron did it. Okay, as far as I know, they just went into Schwarzschild, into Einstein. As Schwarzschild had went into the equation, they allowed this off-diagonal term to the metric and solved the equations and got their equations. Since all of these obey Einstein's equations, that's the way they did it. And as far as we know, they never did this. They never realized that there was this coordinate transformation. Lemaitre certainly did. Lemaitre was primarily interested in cosmology. And that's, of course, where he's made his name in the field. And he was trying to see whether or not you could fit a cosmology in with a black hole. And he discovered these coordinates in trying to match a black hole metric with a dust universe. In other words, a pressureless matter cosmology, uniform cosmology, Robertson-Walker cosmology. In his case, these surfaces of, if you look at this metric, for example, you just get a d tau squared. So that tells you that tau is actually a distance parameter. If you set sigma and r equals constants, well, r is a function of sigma. If you set sigma equals a constant, then you get d tau squared as the only part of the metric. And that's, just the proper time. So tau is the proper time along these radial geodesics. And sigma is labeling of those time-like geodesics. And it turns out that these geodesics are the geodesics of a particle which starts off at infinity with zero velocity. It's, of course, attracted. And so it will start to fall in. And the proper time along those geodesics gives you tau. And if you label those geodesics by the time at which they hit r equals 0, in other words, they hit the central singularity of the Schwarzschild, then that geodesic, then sigma is simply that labeling of the geodesics. So it's a very physical thing.
And I think the tau is the time coming and outgoing to the right.
No, it's the time in his case, it was the incoming time. Okay, along these incoming geodesics.
Tau plus, what's tau minus?
Tau minus is outgoing geodesics. He only wrote down for ingoing geodesics. And if you look at this metric, you see, wait a minute, there's r equals 0, things go haywire. But there's nothing wrong. It looks like a perfectly regular coordinate system. However, if you take, for example, tau plus and sigma plus and ask about these outgoing geodesics, you find out that they have to have left r equals 2m, and infinite time into the past. Just as in Schwarzschild, a geodesic coming out of the black hole comes from t equals infinity at r equals 2m. Here it comes at t equals infinity at the same r equals 2m. Tau minus, on the other hand, is finite coming out all the way down to r equals 0, but it comes, if you send something in, it takes an infinite time in this tau minus time to get in. So although this metric looks completely regular, it's not.
When you say about sending something in, what's that?
Well, you got a black hole here, you drop something in, right?
That or something.
You know, it's falling in. Coming out means that somehow or other the black hole or this thing has shot something out to you. I mean, you can't arrange that because you would have to get inside there to shoot something out. You could imagine that there's this little monster sitting right at the r equals 0 singularity with a little gun who shoots out at you. And you ask, can that come out to me? The answer is yes. It comes out at infinite time according to your tau plus coordinates. It comes out in a finite amount of time if you use the tau minus coordinates. So there's two different kinds of r equals 2m's, a past one and a future one. But this shows that you can make either one or the other completely regular. But it's only one or the other one. He emphasized that this showed that this r equals 1 singularity, r equals 2m singularity, was purely a coordinate singularity. It was strange because there seemed to be two of them hidden in there. One at t equals minus infinity in Schwarzschild, one at t equals plus infinity at Schwarzschild, the future one and the past one. But clearly t had become a nonsense coordinate once you get very near r equals 2m. So people were still confused. He showed that they could be matched onto a dust Robertson-Walker almost trivially. If you now go ahead and use the usual coordinates for a Robertson-Walker spacetime, you can immediately see that tau and sigma go over into what's usually called t and r in the Robertson-Walker coordinates, and there's a completely nice matching between the two of them. He was interested in cosmology, so he had a black hole with this outside being Robertson-Walker, which would collapse. And on the inside, you would have this black hole. And it's sort of a forerunner of what's been called the Swiss cheese cosmology, in which you take you take a dust cosmology, dust because you don't have pressure pushing things off of the geodesics. You take this dust cosmology and you collapse all of the matter inside a sphere into a black hole. Now, outside, it doesn't notice the mass on the inside is the same, so it doesn't notice that anything happened inside. So you can sort of model a cosmology by collapsing a whole bunch of these spheres of dust all over the place to produce these small or big black holes sitting there, which take up the role that the dust that used to be in that hole played. And it's an exact solution. It's trivially easy to do it the other way around, namely to have Schwarzschild on the outside and dust on the inside. That's the Oppenheimer-Snyder solution. 5 years in the future. So Lemaitre, who was one of Eddington's favorite people, he really liked Lemaitre. He was the one that introduced Lemaitre to England, was the one that already had an exact solution for matter collapsing down into what we would now call a black hole. 2 years after Lemaitre published this, Eddington and Chandrasekhar had their big fight. Chandrasekhar said, look, if a star is bigger than 1.5 solar masses, the neutron degeneracy pressure cannot hold it up. And Eddington said, this is just complete nonsense. In the same meeting, he in fact managed to get Chandrasekhar an extra 15 minutes to talk, so Chandra talked for half an hour on his ideas. So this was Eddington had arranged this, and Eddington also arranged right after that to get up and say, this paper that this young guy has done is just complete nonsense. And the chairman of the session refused to allow Chandrasekhar to respond. And why was it nonsense? Because if the star doesn't stay there, what happens to it? I mean, can't just keep collapsing. Well, Lemaitre had already shown, yes, it can just keep collapsing. Incidentally, Einstein, the usual reference to the Einstein-Rosen bridge, which, as I said, I think should really be called the Flamm bridge, had a footnote in their paper which said, there's a well-known metric for an accelerated observer, which was this metric, the Rindler metric, what's now called the Rindler metric. This was in 1935, I guess. They, of course, give absolutely no reference to why this is well known and to whom it was well known, or whether well known means I just showed it yesterday. Rindler knew what he had, and he published it in his textbooks, promulgated it, and so there's some justification for giving him the honor of calling it as his metric, because he made sure that the rest of the world understood about this metric and how this metric related to black holes and so forth. They were still confused. Einstein was still arguing that R equals 2m was a matter sheet somehow or other, that singularity represented some sort of matter sheet. And similarly, in this metric, that rho equals 0 represented some sort of sheet of matter, which attracted stuff towards it. And the reason it looks accelerated, the geodesics come out of rho equals 0 and then go back into rho equals 0 as if it were a sheet of matter. So Einstein was still confused, and Einstein was confused till the end of his life. A few years after this, he published a paper in which he argued that it was, yes, Schwarzschild solution is all very nice, but it could never occur in nature. And the reason is that the last stable circular orbit is over at r equals 6m, not r equals 2m. And therefore, you couldn't have matter orbiting around in circles any closer than r equals 6m. And therefore, one could never get the Schwarzschild solution. Complete nonsense. These are various quotes from Einstein and Rosen paper. So these are all quotes from Einstein and Rosen's paper. This is the footnote in which he argues that if you do this coordinate transformation, you get this metric, which is what we now call the Rindler metric. And even wrote down the Schwarzschild metric in close vicinity to r equals 2m. And if you say if you argue that r minus 2m is very small, and just keep the lowest order terms in R minus 2m, you get just the Rindler metric. This term, you get u squared. The 2m is a constant, but it's much bigger than u squared, so that drops out. Similarly there, but here you get a u squared dt squared, and therefore the Schwarzschild looks just like Rindler near r equals 2m. So they had everything there, and yet somehow didn't recognize that physically this meant that r equals 2m was just a coordinate singularity, just like flat space-time was. It's strange. But then another process came up. People were interested in sticking Schwarzschild into flat space-time. Can one embed this metric in flat space-time? Maybe we can understand it better if we can see it sort of embedded in something we understand, flat space-time. You know, if there's a little parabola there or something like that, then we can sort of get a better intuition. And he went to a lot of work, but the main thing that Singh did was to argue that what he wanted to do was, instead of dr squared over 1 minus 2m over r, take dr over the square root of 1 minus 2m over r and call that capital R, capital Dr, integrate that, and then you would get a term that's just sitting there saying d capital R squared. Then you've got this 1 minus 2m over r in front of the dt squared, and you get this horrible mess for that. And he spent a lot of time arguing that that mess, in fact, reduced down approximately to a very nice form. And so I've written down some of the functions that Singh had. He published it in the Proceedings of the Royal Society of Ireland at the time. And his arguments and his mathematics was a mess. And I don't think almost anybody had the courage to wade their way through it. People knew about it, or some did at least. Werner Israel was in South Africa. They had fled to South Africa because of Hitler, when Hitler came into power. His father was a grocery store clerk. His father got sick. Werner had to interrupt his master's degree in order to help out in the store, etc. But he all of a sudden got this scholarship, and he elected to go to Dublin, where Singh was, to work with him, in part because he knew about this work that Singh had done. Singh's result is to some extent wrong, because he argued that not only r equals 2m was just a coordinate singularity, but so was r equals 0. And he created a coordinate system which went not only through r equals 2m, but also through r equals 0, and you got all this huge tree worth of metrics outside of that. Yes.
So he didn't know it, he just kind of blows off at R0?
Did he know it? I don't know. The question is, did he care? I mean, we look at it and say this is silly, right? But when you don't know what you're doing, it's very easy to take silly things and make silly statements. I mean, that he managed to do it, and what he produced was the very first coordinate system for Schwarzschild, which extended throughout the whole Schwarzschild spacetime. R less than 2m, and also out on the other side, like through the wormhole, if you will, on the other side, a complete universal covering of coordinates for Schwarzschild. But it was, as I said, the equations are a mess. So we get this, everything is analytic. And as we know, an analytic function cannot be zero in a connected set. If you take an analytic function, or if you take a function and you find out that it's equal to zero at a bunch of points which are all connected to each other, then you know that that analytic function is zero everywhere. Einstein's equations are an analytic set of equations. Schwarzschild has zero on the right-hand side. These solutions are the same, are just a coordinate transformation of Schwarzschild, and so they have zero on the right-hand side in the place where they overlap with the Schwarzschild. Therefore, they have to be zero everywhere, i.e. they are solutions everywhere. This is called the analytic extension of Schwarzschild. It's not physical, because in fact, all kinds of other things could happen in regions that are not covered by this stuff you know, but it has to be non-analytic. On the other hand, an analytic function, which is e to the minus 10 to the 10 to the 10 x squared, is as damn close to zero as you're ever going to find for any value of x. There's no way of experimentally telling the difference between them. Okay, but it's not zero, and that's a perfectly good analytic function. So analyticity is extremely strong, but also often very unphysical. Where are we? 1959, Fronsdale, doing almost the same kind of thing as saying, made a better choice. Instead of having capital R squared being R being the distance from the horizon, from R equals 2m to the point R equals wherever you're sitting, he took R squared to be equal to that term multiplying the dt squared, 4 times 1 minus 1 over R. This means I can very simply algebraically solve for R as a function of capital R. And in fact, I can write down the full metric in this new set of coordinates, and it's completely regular everywhere. Now, these coordinates are a little weird because the capital R coordinates go from, R squared goes from minus infinity for little r equals 0 to 4 for little r equals plus infinity. And capital R equals 0 is r equals 2, little r equals 2m. So it's a really compressed radial coordinate. On the other hand, it's a really nice coordinate system in that everything can be solved trivially, algebraically. It's messy, but it's basically a trivial exercise analytically. And you get a metric all in terms of theta, which is like time, and y, which is like a space coordinate. And r is also just a function of theta and y. And there are no implicit functions. So in some ways, the Fronsdale metric was one of the nicest metrics. He was more concerned about embedding Schwarzschild in flat space-time. But on the way, he had this complete set of coordinates. Where am I next? 1960 was the next one. Interesting history. Kruskal and Wheeler were both at Princeton. Wheeler in physics, Kruskal over in the astrophysics building, which sits beside. And as usual, if you're in different buildings, you hardly ever talk to each other, but they were good friends. Unfortunately, both were working on top secret projects, different top secret projects. So they couldn't talk to each other about those things. So they would sit at lunch, they go to lunch at Princeton at the faculty club and chat about all kinds of other things. And one day, Kruskal came up to him and he says, you know, I was playing around with the Schwarzschild metric and I got this result here. Is it interesting? And Wheeler copied it into his notebook and forgot about it. Kruskal then, a year or two later, went off on sabbatical. Charlie Misner, who had just gotten his PhD from Wheeler and was still staying there, got a letter was very close to Finkelstein, who told him about his new coordinates, the Eddington-Finkelstein coordinates, which showed that the r equals 2m was a perfectly regular surface. Misner told Wheeler, Wheeler said, yeah, Kruskal told me something about this. Maybe that's more important than I thought it was. Where's Kruskal's on sabbatical? Okay, he sat down and he wrote up a paper and sent it in to the journal with only Kruskal's name on it. The first Kruskal knew about it was when he got the galley proofs. He very quickly figured out who it must have been that did this to him.
It was obvious.
It was obvious, yes. And got in touch with Wheeler and said, come on, you've got to put your name on this as well. And Wheeler said, no, this was your idea. I just wrote it into the paper form. This is yours. And so this was how the Kruskal metric came into being. So Wheeler-Kruskal, whatever you want to call it, followed basically the second procedure where they got the null rays and went to a coordinate system using those null rays, a universal coordinate system. And because of Wheeler's PR, I think this basically became the fiducial generic coordinate system. At the same time, Shekerish published a paper basically at the same time, completely independently, in which he also derived basically the same one, except in terms, instead of using the null coordinates, he used the Tx coordinates or T psi coordinates, which is just basically V plus capital U and capital V minus capital U coordinates. So that the two groups, the two people, in a sense, deserve equal credit. Wheeler already was giving seminars, apparently in June already. He had given a seminar in which he presented Kruskal's results at a conference and so forth. So Israel in 65, Newman and Pajersky in 71, also found an exact solution. It had the advantage of, just like Fronsdale's, of being being algebraically solvable. So the new coordinates could be written in terms of the old and the old in terms of the new, just in terms of algebraic expressions, instead of Lambert functions and stuff like that. But I'm not going to talk about them much. I'm getting to the end of them. Now, one could go back and say, what happened if Panleve and Goulstrand, or Lemaitre had done something similar back in their days? What kind of coordinates would they have gotten? This, of course, never actually happened, but you can go through these procedures in exactly the same way and find special coordinates. The Panleve-Goulstrand coordinates, by the way, are very, very interesting, because if you take the T equals constant surfaces, you just said T equals constant, so you've now got a spatial surface. That spatial surface is Euclidean flat. Now, Einstein, when he was developing general relativity, knew that the spatial surface had to be flat. It was just time that changed, and that produced gravity. And he was somewhat upset when he discovered in the linearized equations that those surfaces were not flat. I mean, the Flamm thing is this paraboloid. Of course, he didn't know about Flamm, but He had that stuff in his linearized solutions already, that there was something strange, certainly not flat, about the spatial surfaces. The Painlevé-Goldstrand ones were flat. So T equals constant gave you flat surfaces in the Painlevé-Goldstrand. So there's sort of a nice set of coordinates that you can use to get these flat surfaces. Now, where are we? Where am I? So I did a bunch of graphs, okay? So let's take those Painlevé-Goldstrand ones and ask, how do they embed into the Kruskal? So this background here is always all the Kruskal metric coordinates, tau and chi are my coordinates. These are just basically the Shekaresh coordinates for the Kruskal metric. And this is the Painlevé, this fictional Painlevé-Goldstrand set of coordinates. Each of these surfaces are flat, spatial surfaces. And what I've taken is the tau plus and the tau minus, the plus and minus times, and used those as two separate sets of coordinates. The red ones are the tau plus. They refer to particles going out from inside to infinity, and the other ones refer to things falling into the black hole. As always, you get both sides of the metric. Those are, in a sense, the two sides that Flom found in the spatial part of the metric. Also occurs for this maximal extension, which is this one. These are the Singh coordinates. They look like nice time and space, somewhat curved with respect to the Kruskal metric. These are the Lemaitre coordinates, the spatial parts of the Lemaitre coordinates. One doesn't need null rays. One can get spatial geodesics or temporal geodesics and use those as global coordinates as well. And these Lemaitre ones are, well, these are, I guess, time-like surfaces. These are the Eddington-Finkelstein one. Each of these may have some advantages or disadvantages. But one of the things that I'm trying to get across is that in general relativity, those coordinates are not anything physical. They're up to you. Just choose whatever makes your life simplest, or choose them so that they have some nice features, like, flat spatial slices. And it's one of the hardest things for students to get a handle on, because suddenly it feels as though you're on a raft on a stormy sea, right? Where in the world do you put your feet? You're so used to thinking of coordinates as meaning something.
Yeah.
And in general relativity, coordinates mean basically nothing. What you have to do is to use those coordinates to calculate. But there's all kinds of different tortoise coordinates. I mean, for example, if one does the Kruskal one, then it's r plus 2m log r minus 2m, right? If you do the Painlevé, I think it's the Painlevé-Goldstrand one, then it's the log of the square root of r minus 1 over the square root of r plus 1. You can get all kinds of different logarithms. They always have that r minus 1 goes to, at r equals 1, you've gone off to infinity. But as I said, you could have logarithm of square root of r minus 1, which for I think it's Painlevé-Goldstrand is what you get there.
But this means that if I go from one of those coordinate systems to the other one, I just can do transformations and I get the same, and this is proven, like they are all same.
Yeah, they're all just coordinate transformations of each other. But what you actually get in there, the tortoise coordinates, as I said, is this r plus 2m log r minus 2m divided by 2m, if you will. That's the usual tortoise coordinates that Wheeler likes to call tortoise coordinates. But if you do Panelevi-Goulstrand, finite time-like things falling in, then I believe you get a term like logarithm of the square root of r minus 1 over the square root of r plus 1. Yes. Here, the physics is identical for all of these, but they all look very different. And that's really hard for students to sometimes get a handle on. So that was one of the points that I wanted to emphasize here. So these are the null coordinates. It has an off-diagonal term. Einstein didn't like that. So he, in his assumption of his linearized theory, threw out anything that had an off-diagonal term. Simplified the equations, of course. This metric, the only place basically where r comes in is this term. And in fact, this is a solution of the linearized equations. It's also a solution of the full equations. The same metric is a solution of the linearized equations and of the full equations, which is pretty amazing because you've all been taught that gravity gravitates. You have a gravitational field here. That gravitational field, Einstein says that gravitational field also gravitates and produces part of the gravitational field. This is a linearized solution. There are no extra terms. There is no gravity gravitates. And yet it's a solution of the exact equations.
This is correct just from 4D or?
What?
This is correct from 4D or?
Yeah, well, there may well be correct. I live in 4D. You live in 4D. So yes, this obeys Einstein's equation, empty space Einstein's equations. So that tells us, which we sort of knew, because usually one finds that, GU linearized is equal to, T and U plus then some gamma kind of terms, which are nonlinear terms. One looks at that and then says, okay, these terms are the energy momentum tensor of the gravitational field. Landau and Lifshitz, for example, look at that way. But as they say, those terms depend on the coordinate system. We've always known that. Landau and Lifshitz knew that and so forth, and they will choose some particular coordinate system, for example, the Donder coordinate system or whatever, in order to simplify them, but you still get those terms. But in this null coordinate system, those terms don't occur at all. Gravity doesn't gravitate. So whether or not gravity gravitates can depend. This isn't true generically. As far as I know, nobody has ever proven that generically one can always write down solutions and find a coordinate system such that those right-hand terms disappear. I don't think that's true. But certainly for these special situations, and in particular for a black hole, it is true that gravity doesn't gravitate.
All black holes are does not exist.
As solutions, they certainly do exist.
A solution, right? But if gravity doesn't gravitate, there might be that it can be some inconsistency with the property.
Well, I mean, one can show. I mean, Birkhoff showed that if you assume spherical symmetry, that Schwarzschild is the only solution. And furthermore, one can argue that any solution will asymptotically, if you collapse them, it will take away quantum mechanics, it will asymptotically approach Schwarzschild. So if you wait a long time, you'll get Schwarzschild. So black holes, that those spherically symmetric solutions do exist in that sense. And yet, gravity doesn't gravitate. So there's all kinds of little things about general relativity, and in particular, the coordinate freedom in general relativity, that are especially designed to trip up students and to confuse students. And by students, I mean me, the 78-year-old student.
Professional student.
I still get very confused. I mean, this was a point that I only realized last year when I was teaching a general relativity course. Wait, I had done this before and so forth, and then all of a sudden I said, wait a minute, doesn't this mean blah, blah, blah? But at this point, I think I better quit. I think I've gone over time. I'm not even going to look at my watch.
Thank you very much, Bill.